Hi, my name is Noson Yanofsky. This is Theoretical Computer Science. We're doing section 1.2 of Sipser's book, and this is all about non-determinism. I'll explain that in a minute, but let's review what we did. We started talking about finite automatons, okay, and finite automatons are machines that recognize regular languages. Now, whenever you have a computer, the first thing you want to do is get a better computer. You always want to get the better one. Okay, so what we're going to talk about is another type of finite automaton called a non-deterministic finite automaton. Okay, and I'll explain what that is. And it's somewhat better. It's going to take less states to do things. It's going to be more intuitive of what to do than the types of finite automatons that we did talk about. Okay, so the type of finite automatons that we did talk about were deterministic. Okay, I didn't call it deterministic because we didn't have anything deterministic. Okay, and they went very nicely. You start off in a start state, and then you go to another state, and then you go to another state, and then you go to another state. As you're reading the words, you go to another state, and you go to another state, and then if you end up in a doubly accepting state, when you finish reading the word, then the word is accepted. If you end up in a non-doubly circled state, a non-accepting state, then it's not accepted. That's very good. Let me give you the intuition of non-determinism. Non-deterministic. Okay, and there you start at a starting state. Okay, but from that state you might go to a few different places. Okay, so you might go to this place, you might go to this place, you might go to this place. Okay, and then the next state you might go to this place, you might go to this place, you might go to this place, or this place, you might go to this place. And then the next thing, you might go here, here, here. You might go nothing there. You might go here. You might go here. You might go there. You might go there. Okay. And what you do is, at every single state, you can you have the possibility of branching out more than one place. Okay. So, in some sense, it's massive parallelism. In other words, you could do more than one thing at one time. And you go on reading the words, and if any one of these paths get you to a double accepting state, then the word is accepted. A doubly circled state, an accepting state, then the word is accepted. Any one of these whatsoever get you to that doubly circled state, you're done. You're good. Okay? So that's what the difference is. So obviously a parallel computer is better. A computer that can do more than one type of processing is better than a single one. But we'll discuss the pros and cons as we go along. Okay? Okay. The main point is a non-deterministic machine, in a deterministic machine, you give me a state. You give me a letter, I'll tell you what other state to go to. It's a single other state to go to. You give me a state, you give me a letter, I'll tell you what other state to go to. In non-determinism, you give me a state, you give me a letter, and I'll give you a subset of states to go to. That's the main difference. You have a bunch of possible states to go to. Okay? So it seems much more powerful. Okay. Okay. I did not call the previous things deterministic, but those were DFAs, okay, deterministic finite automatons, and now we're going to do NFAs, non-deterministic finite automatons. Okay, the words are too big to write, so we'll give their acronyms. Great. So again, what we're going to start doing is a bunch of examples, and we have a bunch of examples. Then we'll give you the exact theory of it, of the definition. Okay, so let's write an machine. Let's do an example. The alphabet is 0, 1. Okay, and the language that we want to mimic is W such that the third to the last letter is a 1. The third to the last letter is a 1. Okay, so let me just give it to you and show you how it works. It goes as follows. If this is the third to the last letter, then we want it to be a 1. Otherwise, the second to the last letter and the last letter, we don't care. It's either a 0 or a 1, but the third to the last letter is a 1. Okay. Question: how do you know if the letter you're reading? Remember, the computer reads the letters from the beginning to the end. How should the computer know if the one they're reading is the third to the last one or not? And the answer is it doesn't. It doesn't know that this is the third to the last. What it has to do is it has to try and say, oh, here's a 1. Is that the third to the last? Is that the third to the last? But at the same time, it should stay there and wait. Also, this one that you see might not be the third to the last one. And so it has to stay there also. Now notice, when you're in this state and you see a 1, you go to 2 places. No longer can I do this with 1 finger. Okay, I need 2 fingers to tell it where to go. Okay, and so we're going to do that. Also, if I see a 0, I should stay here. Wait. Okay, great. Question: what happens if I get here? Okay, I bounced along and I get here and I have another letter. Well, this doesn't tell you where to go, but actually it does tell you where to go. Where it tells you, it says, don't go anywhere. Die. This path that's going if it sees another letter, it dies. It goes to no states. It goes to the empty state. Okay, which means it doesn't exist anymore. Okay, so we're going to do a few examples first. Okay, so let's try this word. 1, 1, 0, 1, 1. Okay, so look what happens. I'm here. I do 1. And I'm here. I'm in Q1 and Q2. Great. And now I see another 1. So this goes here, and this goes end here, and this 1 goes here. So I'm now on first, second, and third base. Let's start that over. I start here, I see a 1, I go here. I see another 1, then this guy splits into 2, I'm here and here, and this guy goes to here. Great. Then I see a 0. Let's see what happens. I have to check all the paths. Each person is individual. This 0 goes here. Great. This 0 goes here. Great. And this 0 goes here. So now I'm in first, third, and fourth. Okay? First, third, and fourth. Next, I then see a 1. Okay? Well, he dies because there's no place to go. He goes here. Okay? First, third, and fourth. The third goes to fourth, and the 1 goes to 1 and 2. So now I'm 1, 2, and 4. Okay? Now you see a 1 again. He dies. He goes here, and he splits to 3. So we're in all 3. Okay, we're going to have to do this in a chart. So let's do this in a chart. Okay? We're going to read down. We see 1, 1, 0, 1, 1. When you see the 1, you're in Q1. I'm sorry. Before you see the 1, you start off the starting state, you're in Q1. Then you see a 1, and you go to Q1, Q2. Okay. Then you see another one. Let's see what happens. The Q1 goes to Q1 and Q2. The Q2 goes to Q3. Great. Then you see a 0. So you're in 1, 2, and 3, and you see a 0. Okay, let's do the 1. The Q1 stays in Q1. The Q2 goes to Q3. The Q3 goes to Q4. Great. Then you see a 1 again. So let's see. The Q1 is going to go to Q1 and Q2. The Q3 goes to Q4. And the Q4 dies. Finished. Next. Then you see another one. The Q1 goes to Q1 and Q2. The Q2 goes to Q3. And the Q4 dies. That's it. But the main point is, at the end of this, Q1, Q2, Q3, you're at here, here, and here. You're not in an accepting state. The word is not accepted. And the word is not accepted because the thing is over here. Okay? Can we just change the word now? Okay? Let's put another one now. Let's put another one. Now the third to the last thing is a 1. Now it'll be accepted. Let's just see. Let's just see. The Q1 goes to Q1 and Q2. The Q2 goes to Q3. And the Q3, the one that was in Q3, sees a 1, goes to Q4. This is an accepting state. The word's accepted. Okay? That's the way it works. Okay? By the way, I'd like to do a transition function for this. How do we write the transition function? Well, we have 4 states, Q1, Q2, Q3, Q4. We have 2 letters, 0 and 1. Let's see how that goes. I'm going to do it this way. Q4, you see 0, you go to the empty state. Q4, you see a 1, you go to the empty state. Q3, you see a 0 or a 1, you go to the subset that has a Q4. The subset that has a Q4. Q2, okay, you see a 0 or a 1, where do you go? The subset that has a Q3. The subset that has a Q3. Okay. Q1, you see a 0. Q1, you see a 0. You stay at Q1. That's that. Okay. And here's the main part of nondeterminism. We actually had the main part down here also. This fact that you can send it to any subset, including the empty subset, that's already done. But this is the main part of the non-deterministic feeling of it, is Q1, you see a 1, you go to Q1 and Q2. Okay? The main part is, beforehand, you gave me a state, you give me a letter, and I'll tell you what state to go into. And now you give me a state, you give me a letter, and I'll tell you what set of states to go into. Okay? Okay. By the way, if you close this off and you close this off, this looks very much like a deterministic Turing machine, a finite automaton. And in fact it is, if you just close off, just look at these things. Because at every state you're going to exactly one place. Going to exactly one place, going to a subset that has exactly one element, is exactly what we call deterministic. So that's very nice. Okay? More examples. Okay, let's do this. Okay. Any B and W is followed. Okay. The alphabet is A, B, and C. A, B, and C. And it's those words such that any B is immediately followed by a C. Any B is immediately followed by a C. Okay? And we're going to see Oh, sorry. Before we do that, let's think about the last example. I don't want to edit anything. There's a way of writing these things. So remember, the third to the last letter is a W. W such that the third to the last letter is a 1. Okay? There's a way of writing this called a regular expression. We're going to see formally what regular expressions are in section 1.3. But I want to just do every single example I see, I want to write it as a regular expression. And you'll see why. Because you can almost figure out the finite automata, the non-deterministic finite automaton, by looking at the regular expression. You can almost go the other way also. Okay? So the way we write this is, the third to the last letter is a 1, is as follows. You say as follows. 0 or a 1 star. That means any amount of letters. And within this, you can choose a 0 or 1. 0 or 1. So first time you can choose a 0, the second time you can choose a 0, the third time you can choose a 0, fourth time you can choose a 1, fifth time you can choose a 0, any amount. Then have a 1, and then have 0 or 1. That's the second to the last thing. And then have a 0 or a 1. That's the last thing. Okay? This expression describes the same language as that. Okay? Any amount of zeros or ones, followed by a 1, followed by a 0, 1, or a 0, 1. I just want to write it another way. The alphabet is 0, 1, so you can write it like this. Any word, followed by a word, followed by sigma squared. 2 more letters. Okay? Okay. Just want to do it one other way, just to get a feel. These are different ways of expressing the same thing, but they're very nice. Okay? You can express it like this. 0 or 1 star, followed by a 1, followed by 0, 0, or 0, 1, or 1, 0, or 1, 1. Okay? Maybe there needs to be spaced a little bit better, so you can see the different things. 1, 2, 3, 4. In other words, any word followed by a 1, followed by the last 2 letters. And there are 4 possibilities for the last 2 letters. So this is just a feel of getting these regular expressions right. Great. Okay, so we're going to do that for now on. Every time we see an example, we're going to do that. But I forgot about that one. So now let's do this. The alphabet is A, B, or C. Any B is immediately followed by a C. Let's go through some words that are in it. A, C, A, B has to have a C afterwards. A, B has to have a C afterwards. C, C, C. That's in the language. Okay? A, B, A, C, A. That's not in the language. Okay? Because it has to have, right after the B, it has to have a C. Not any time after. Okay? And the answer is as follows. Let's go through this. Question: is the empty word in here? And the answer is yes, because there is no B. If there was a B, there would be a C following it, but there is no B. Conclusion: the empty word is in it. Okay? Okay? And what happens next? What happens if there's an A? Well, just stay there. If there's a bunch of A's, that doesn't bother me also. Okay? Another thing, if there's a bunch of C's, that doesn't bother me. The only thing that this says is, if you have a B, then you better go and wait for a C. That's it. Okay? That's it. Now that's pretty amazing because you did this in just 2 states. Okay? You can do this in the deterministic thing, but it'll be probably 4 states. But notice what happens. If you have a B, then you go there. Okay, first of all, It's hard to see the non-determinism here, but you have it right here. Question: what happens if I have a B and then I have another B? Where should I go? Well, the answer is you're here and you die. This thing dies. Okay? What happens if you're here and you have an A? You die. Okay, so that's very interesting. The only way you can get back here is if you have a C. Let's just do this. Okay? A, C, A, B, C. A, B, C, 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 C. That ends up here. It's accepted. Let's do this one. A, B, A. He dies. There's no place to point where he is now. And so you can read this all you want. C, A, he's not anywhere. He's not, definitely not there, but he's not anywhere. And so he's dead. Okay? Let's write this as a regular expression. Okay? And it's very, very cool. It's as follows. A union C star. In other words, start off with any A's or any C's. Then, if you have a B, you must have a C right afterwards. And you can have as many copies of that as you want. Okay? But once you're finished with that, you go back again and you could have as many copies of A's or C's again. But every time you have a B or C, you have to go like that. That's it. Okay. These regular expressions are very interesting because I told you, they're finite automatons, and in that sense, they have a little bit of all the computing power. You write things like that, that means sequential processing. First I want to see a B, then I want to see a C. You write something like this, A union C, that corresponds to parallel processing in some sense. An A or a C. Try this or try this. And the stars correspond to loops. So you have sequential processing, parallel processing, and loops. That's the basics of computers, in some sense. Okay, great. Let's do another one. Oops. The alphabet is A, B, and C. And the language is write it like this, W such that W is equal to A, B, C to the N, where N is greater than or equal to 0. So this means it's ABC, it's the empty word, it's ABC, it's ABC, 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 ABC. Okay? But again, you see the non-determinism here, it's going to come out very simply. First of all, notice this could be a 0, which means W is equal to ABC to the 0. To the 0 means it's the empty state. Not this empty state, the empty word. Okay? Okay? Then, if you see an A, you better make sure that you see a B afterwards. Okay? And then, if you see a C, you go to the accepting state. Then you can see an ABC again, and an ABC again, and an ABC again, and an ABC again. Notice there are no garbage states in non-determinism, because you don't have to say, oh, look, this didn't happen, go to the garbage state and stay there. You can just let it die. For example, if I see an A, B, and then I see an A again, it dies. So I don't need a garbage state. And that's it. Okay? By the way, as a regular expression, this is A, B, C, star. Okay, great. Now another example, which is going to be a different answer. You have to rewrite this. So rewrite this. Ready? N is greater than 0, not equal to 0. Okay. Notice now that the empty word is not accepted. So The empty word is not accepted, so that's not an accepting state. Okay? What do I want? I want to see an A, then I want to see a B, then I want to see a C. Okay? And if I see an A, B, C, that's accepted. Okay? And then if I see another A, I go here. Not here, here. I see another A, and I start waiting for another A, B, C. A, B, C. So that's this state. Okay? So sometimes we have to be able to do this. Question, how do I write this? Okay? And I'm going to write it two different ways. I'm going to write it three different ways. A, B, C followed by A, B, C star. In other words, have one ABC and then have as many ABCs as you want afterwards. Or I can write it another way. Have as many ABCs as you want, but just make sure that you have an ABC also at the end. Okay? But these two things can be written as follows. There's a shorthand to writing these two things. ABC plus. Star means any amount including 0. Plus means positive amount. 1, 2, 3, 4, etc., etc. Okay? So that's a nice example. Okay. Let's do another one. The language is equal to words such that the word is equal to A, B, C, followed by an X, followed by CBA. Wow, hold on. Where X is a member of sigma star. In other words, the word should start with ABC, then it should have anything it wants, then it should finish with a CBA. Okay? Okay, and the way you do this is very simple. You can almost read it from that. By the way, as a regular expression, this is just A, B, C. Okay. A union B union C star. Have the word start with an A, B, C, then have an A or a B or a C, as many as you want, then C, B, A. That's the regular expression. And you can almost write the finite automaton with this regular expression. It's an A, B, C. We'll do this in a second. And then I want you to finish the word with a C, B, A. And then it's an accepting state. The main point is here. This is A, B, C. You can almost read it. A, B, C, A, B, A, B, C, A, B, C. A or B or C, do that. C, B, A, C, B, A. Okay? The non-determinism comes right here. In the beginning, I see an A, B, or C, I keep on going. If I see an A, B, B, then I die. I die right here. A, B, B, I die. A, B, C, I die right here. Never go further. Okay? But you see the non-determinism here also. If I'm here and I see a C, I don't know, hey, is this the end of the word or not? This new C that I just saw, is this the beginning of the next, of the last three letters of the word? I don't know. So what I do is I try this, and I break off and I try both of them at the same time. Okay? Sounds good. Okay, great. How about this? The language is the letter A. The word A. This is the stupidest language in the world. It has one letter, and that letter, it has one word, and that one word consists of one letter. Okay? Well, it's very simple to write this finite automaton. It's exactly that. Okay? And if you have any letter afterwards, it dies. If you just have one letter, it's good. Okay? That takes care of that. And by the way, what about this language? This is the world's stupidest language. What did we say a language is? A subset of words. How about the empty subset of words? Well, that becomes that finite automaton accepts that language. So that's very good. Okay, we'll see some more interesting cases in a minute. Okay, we did 5 examples or so. Let's go through a little definition, a formal definition. Definition. Okay, now I'm going to be a little bit quick here. You're going to look in the book, you're going to see it, whatever, but we're basically modifying our definition of a finite automaton, which was a deterministic finite automaton, and changing it here to what's a non-deterministic. A non-deterministic finite automaton is, again, a 5-tuple. Q, a set of states. Sigma, a set of alphabets. An alphabet. Delta, a transition function. Q0, a starting state. And F, a subset of accepting states. Great. Now, everything is exactly the same as before, except for the transition function. Don't write this, so again, everything else is the same, let's just do the transition function. Stop, don't write this, let's remember what the transition function was before. It said, you give me a state, you give me a letter, and I'll tell you what state to go into. That's what we had before. That's a deterministic. But now, let's do non-deterministic. It's almost the same, but here's the difference. You give me a state, tell me where you are. You give me a letter, and I'll tell you a subset of states to go into. That's the power set function, pregnant P. The script P, power set function. A subset of states. Okay, so a typical thing would be something like this. I'm in Q37. I see the letter B. I want you to go to Q52, Q38, Q19. It's a subset of states. That's the typical example of a transition function. Okay? Okay, great. Great, so non-deterministic finite automatons seem a lot cooler than anything else we've seen so far. That's fine, but you know what? I can even get more cooler. Okay, so we have a new concept here. They're called Epsilon-moves. Okay, and what it says is as follows. If I'm in this state, Q32, and I see an A, I can go here and here. Okay, that's clearly non-determinism. Okay, you can go here and here. Very nice. But now we have something else that can happen also. I can see nothing and go here, here, and here. These are called epsilon-moves. Again, epsilon is the empty word. Okay, an epsilon-move can go these 3 places. Okay, what this means is as follows. When I'm here, without reading any letters, I'm automatically here, here, and here. You're never here by itself. You automatically, break apart into more than one of those places. Okay? Okay, so let's do another, let's use a NFA with epsilon-moves. Okay, let's do it with this. Let's try to do it for this regular expression. A bunch of zeros followed by a bunch of ones followed by 0 plus, followed by one or more 0. Okay, I'm going to write it another way just to get a feel for it. A bunch of zeros followed by a bunch of ones followed by 0 and a bunch of zeros afterwards. Okay, now I want to show you how to do this. Okay, it's basically, notice that the word could start with a 0, this 0. By the way, just having a 0, the empty word is not accepted here. The empty word is not accepted. Okay, but I can start with a bunch of zeros, as many as I want, then, but at every point, also be here, and try to have as much ones as you want. Okay, so when you're here, you're automatically here. By the way, it doesn't go the other way. When you're here, it doesn't mean you go back. Okay, okay, and follow that by a 0, and then by a bunch of zeros. Okay, that's an accepting state. Notice just the letter 0 is accepted here. Here's the way it works. You start here. When you start here, you're automatically here. You see the 0, you go here. This goes here. You're going to be in these two states, but here you're accepted. That's it. Okay? I'd like to show it to you one other way, just to get a feel for these epsilon moves. Question: how do you start this word? Well, you could start with this bunch of zeros. Okay. You could start with a bunch of ones. And you could start with a 0 and a bunch of zeros afterwards. So here you really see what these epsilon moves. It says, look, I'm here. I don't know how he's going to start his words. He could start with a bunch of zeros, he could start with a bunch of ones, or he could start with the final bunch of more than one 0. So that's that. And so expressing or, that's the way you do it. Okay? It's a nice way of doing that. Okay, great. I'd like to show you the transition function. Okay, I'm finished with this. I'd like to show you, so we have a new type of non-deterministic finite automaton. They're called Epsilon-move finite automatons. They're non-determinism, and they have this epsilon. Okay? It's again a state, an alphabet, a transition function, a Q0, an F. Okay? But the transition function, let's write it the 3 ways. Okay? You give me a state, you tell me what letter you're seeing, and I'll tell you what state to go into. That's a DFA. An NFA is, you give me a state, you tell me what letter you're looking at, and I'll tell you what set of states to go into. Okay? And finally, an epsilon-move NFA says as follows. It's a little bit more complicated. It says, you give me a state, and tell me what letter you're looking at, or tell me that you're looking at the epsilon move. One of these two things. What letter you're looking at, or an epsilon move, and I'll tell you what set of states to go into. Okay? And just the book uses this following strange notation. They say, call this sigma with a little extra epsilon in it, okay? And tell me what to do. Okay. Two more little things to catch up with. Question. This is different than this. This is the language with no words. 0 words, the empty words. No words. The empty set of words. This is the language which has one word in it. The one word is the empty word. Okay, it's different, they're different, they're not equal. They're not equal. Okay, how do you write this as a finite automaton? How do you get a finite automaton to accept this? This is exactly it. Okay, you just say, stop. If you give me no letters, then I stay here. If you give me a letter A or B or C, I die. But no letters, I stay here. Okay, that's one thing. Okay, so that's another cute little finite automatons. You have to understand these 3 levels. Okay? And you have to understand as follows, and this is very important. We're going to see this in a few minutes even more. There are DFAs. Now, DFAs are special types of NFAs. Let's go through why. Because an NFA can go to a set of things, okay, and a DFA also can go to a set of things, but the set is a special type. It has one element. It's a singleton set. Okay? So DFA says, you give me a letter, you give me a state, I'll tell you what state to go into. Let's restate, let's re-say that. You give me a letter, you give me a state, and I'll tell you what state, what set of singleton set to go to. That's what a DFA. An NFA, you can go to a whole bunch of states, a subset of states, including the empty states. Okay? But then you have something bigger than that, and those are called NFAs with epsilon-moves. It says, not only will I go different places if you give me a state and you give me a letter, but if you give me a state and you give me the epsilon, you give me the empty word, I'll also tell you where to go. Okay? So sometimes I'll tell you where to go. Okay? Okay? If you give me a letter like this, I'll tell you where to go. Well, if I don't use that epsilon move, I have exactly an NFA. So an NFA is a special type of this. This is more powerful because you can also I can also tell the transition function, hey, I have an epsilon, okay, where should I go? But if you don't use that, you get an NFA. So this is a 3-level hierarchy of your finite automatons. Very nice. Okay? Obviously, this is the most powerful, and you're going to have the least amount of states if you do this. This is like programming, super programming. As opposed to that DFA, you can have a lot of states, and we'll see why in a few minutes. Okay, great. One more idea, and then we got it. I mean, the section 1.2 has a lot of stuff in it, but what does it mean for NFA machine Q sigma delta Q0 F? So what does it mean for a machine to accept a word W, which is equal to W1, W2, W3, Wn? Question mark. Okay, we did this for finite automatons. We saw what it means for a word to be accepted. Okay, now we did this for deterministic. Now I want to do it for non-determinism. Okay, well, go back. You'll see it's the same, almost the same thing. Okay, so let's write it. There's a sequence of states. Okay, you're reading this in the book. Okay, R0, R1, R2, Rn. Okay, and it satisfies three things, just as before. The first thing is obvious. R0 is equal to Q0. Start at the starting state. Okay. The third thing is obvious too. R0 is a member of F. End up in an accepting state, a doubly circled state, an accepting state. Okay. Stop. Put your pens down. What we had before was, I'm going to write it a funny way, Ri plus 1 is equal to delta of Ri, comma, Wi for I equals 0 to n minus 1. Just don't write that. What we had before was we bounce around using our single finger because we're always in at most one state at one time. And we say, oh, if you're in state Ri and you see the next letter, go to the next state. So that's describing this sequence of states. You're in this state, you see the letter, you go to the next state. You're in this state, you see the letter, you go to the next state. You're in this state, you see the letter, you go to the next state. Okay? There's always one state. Okay, but now we're in an NFA, non-determinism. So this, by the way, notice I wrote it backwards. Okay, I wrote it before as delta Ri is equal to Ri plus 1. I wrote it backwards for a reason. NFA, this is no longer a state. What is it? It's a set of states. So rather than writing equals, I'm going to write it like this. This is a set of states. I want this next state to be one of those states, one of those possibilities. So we're going to have Ri. I'm going to see the letter Wi. Okay, and I can go to any one of these states. And the point is, this sequence is going to be one of these. A sequence, what does this mean? It means this is some type of computation going along. And this is exactly what these states are. It's a computation. Okay? What's a computation? It's a sequence of steps that your computer's in. Okay, great. So that's really the first part of section 1.2, going through what is nondeterminism. Okay, the second part of section 1.2 is saying, okay, what's better, nondeterminism or determinism? Okay, well, it depends what you mean by better. What's better, nondeterminism with epsilon-moves or determinism? We'll see what you mean by better. Okay, give me a minute. Okay, so continuing section 1.2. We have this notion of nondeterminism, nondeterministic finite automaton. You might think, hey, these are great things. You could do it in fewer things. Maybe there's maybe these non-deterministic languages, these non-deterministic finite automatons, or these non-deterministic finite automatons with epsilon-moves, maybe they can recognize different languages than can only be done by a mere deterministic finite automaton. Answer: no, wrong. Whatever can be done by those other fancy machines can also be done by an old-fashioned deterministic finite automaton. And that's what we're going to do for the next hour, okay, and prove it. Okay? So here's a nice finite deterministic, here's a nice non-deterministic finite automaton. What I want to do is I want to make a deterministic finite automaton that does the same thing. So, but before we do it, I want to show you the idea. The idea is as follows. Let's say I see the 1 in the word. Well, look what happens. I start here and I see a 1, then I automatically go here. So I go into the state Q1 and Q2. Both states at the same time. Now, let's say I see a 1 and a 1. So then I start here and I'm here. And then I'm in state 1 and 2, and now I see a 1 again. This one goes here, and this one goes here, and splits here. So then I'm in state 1, Q1, Q2, and Q3, all at the same time. So if I see these two things, these two letters, I am in all three states at one time. Great. Now, let's say I see 1, 1, 0. Let's see what happens. So I'm in state 1, 1. I'm in state which I see 1, 1, which puts me in state 1, 2, and 3. And now I see a 0. This guy goes, dies. This guy goes here, and this guy goes here. So then I'll be in state Q1 and Q3. Okay, great. By the way, this is accepted because it's in Q3. There's one guy here, but there's one guy there. Conclusion, okay, the string 110 will be accepted. Okay, but the idea is as follows. This is an NFA. I want to convert an NFA into a DFA. Okay? The idea is as follows. Rather than having different states, make one state to be the set of states. And I'm going to have one state this set, and I'm going to have one state this set. Okay? So the states of the DFA will be subsets of the states of the NFA. Let's restate that. The states of the DFA will be subsets of the states of the NFA. Okay, great. So let me show you how to do this. Okay? There are 3 states in the DFA. How many subsets are there of an element with 3 sets? Okay, so you have to remember your stuff with the power set, but basically there's going to be 8. Let's go do it. Okay, we're going to have the state called Q1. We're going to have the state called Q2. The set with Q2. We're going to have the state called Q3. Okay, we're going to have the empty set. The empty set is also a subset of the states over here. Okay, we're going to have a state called Q1, Q2. We're going to have a state called Q1, Q3. We're going to have a state called Q2, Q3. Okay, and we're going to have a state called Q1, Q2, Q3, all 3 of them. Okay, great. Okay, so we have 3 states in our original NFA, and now we're going to have 8 states in our DFA. This is what I said. You might have the same DFA. DFA can do the same thing, but an NFA can usually do it in fewer states. Great. Now, what's our starting state? Well, it's going to be this, because you start right here. Okay? And now what we're going to do is we're going to fill in the arrows. But we're not going to do every one of them, and I'll explain to you why in a second. Okay, but let's start here. You're in Q1, and you see a 0. Where do you go? Well, it tells you where to go. We're going to have this DFA mimic this DFA. I'm sorry, we're going to have this DFA mimic this NFA. Okay? So if you see a 0, you go there. That's very simple. That's agreeable. The next part is the key core of it, so let's do that. If I see a 1 here, where do I go? Well, look what happens. I do the 1 here, and I do the 1 here. So I end up here. This is the state that has Q1 and Q2. Okay, so that's different than this. But the main thing is, this is a DFA. I'm only going to one place. Which place? The place that represents here and here. Okay, good. Now, I don't want to do this because I want it to follow here. Let's say I'm here. I'm in Q1 and Q2 and I see a 0. Where should I go? Well, he goes to Q1 and he goes to Q3. So if I see a 0, I'm in Q1 and Q3. I'm in Q1 and Q2 and I see a 1. Where do I go? Well, this one goes here, and this one goes here and here. So I'm in 1, 2, and 3. So far, so good. Okay. Great. Let's go on. I'm in Q1 and Q3, and I see a 0. Where should I go? Well, the Q1 stays there, and the Q3 dies. So I'm left with this. Hold on. Let's do that again. Yep, now you got that right. Okay, good. Next. Okay, I'm in Q1 and in Q3 and I see a 1. So the Q3 dies and the Q1 goes to Q1, Q2. By the way, what language does this accept? We saw something very similar to it a little bit earlier. What language does this accept? And the answer is as follows. The second to the last word is a 1. I'm sorry, the second to the last letter is a 1. I don't care what the last letter is, I don't care what the beginning is, but it's a 1. So it becomes this. This is 0, union 1, star. Start off the word in anything you want, then a 1, then a 0, union 1. Okay, great. Let's finish this up. Okay, we could also write this like this. Sigma star 1 sigma. Okay, now I dealt with this, 0 and 1, that's very good. Now I'm here. Okay, I'm in state 1, 2, and 3, and I see a 0. Where should I go? Well, this guy 0 will die. He'll go to Q3, and he'll go to Q1. So it goes to Q1, Q3. Great. Now, I'm in Q1, Q2, and Q3, and I see a 1. He dies, he goes here to 3, and he goes here and here. So it stays 1. Okay, great. Now, what about this state and this state? Well, I can actually fill it in. If you want, I could fill it in. But there's really no reason to fill it in. Why? Because, on this one also, there's no reason to fill this one in also. Why? Because I'm never going to get there. I'm going to start here and I'm going to bounce around, but I'm never going to get there. I'm never going to get to here and here. Let's, for the hell of it, just do it. I'm going to do it in a different pen so we can do this. Let's do Q3, and I see a 0. Where do I go? There. Q3, and I see a 1. Where do I go? I die. There. I'm here. I'm not on any state whatsoever. Then I see a 0 or a 1. Where do I go? I stay there. This is always going to be the garbage state. This is what we said. An NFA doesn't have a garbage state, but if I'm going to mimic it with a DFA, I'm going to have the garbage state. And what's the garbage state going to be? It's going to be the dead state, the state where you can never go out. Okay? Because once you're dead, you're never undead. Okay? We could do this also. Q2. Q2 and you see a 0, you go to Q3. Q2 and you see a 1, you go to Q3. Okay. But again, these things, I don't even have to write them because I'm never going to get there. Okay? And so we can rewrite this whole thing. This is going to have 1, 2, 3, 4. And let's see if we can rewrite it. We don't even have to rewrite it. We can just erase. You have to rewrite it because you don't have a whiteboard. You have a piece of paper. So let's just erase. Okay, but you should rewrite it in a neat way. Now let's see if this accepts the same language. You ready? Start off with a bunch of zeros. Fine. I'm looking for the second to the last number should be a 1. So if I have a 1, go here. And say, this says, look, I just saw a 1. There's two options. One option is it's the second to the last thing. So let's see what happens. Oh, I forgot to say, what's an accepting state here? Anything that has a Q3 is an accepting state. So that's an accepting state. and that's an accepting state. Okay, let's go through it. I see a 1, then that could be the second to the last thing. If there's a 0 afterwards, that's an accepting thing. That's very good. Okay, and we stop. If there's a 1 afterwards, that's an accepting thing, and I stop. Okay, but now let's say, so I had a 1. Let's do this, and then I have a 0. Great. Okay, I have a lot of other things, and then I have a 1 and a 0. So then I'm here. That's very good. Now, if I stop reading anything, then this is acceptable because the second to the last letter is a 1. Very good. But what happens if I next see another 0? Okay, if you next see another 0, then you go here because you're not accepted anymore. It was the second to the last element was a 1, but now the second to the last element is a 0. Don't do that. You go here. Okay? Okay? Now, if I see a 1 again, that could be my second to the last element. If I see a 1 again, I go here. If I see another 1, so this stage tells me I just saw 2 1s. This stage tells me I just saw a 1 and a 0. Okay? Anyways, you can follow this along, and you'll see that this is the same language as this. It's very, very nice. Okay, great. Anything else? Okay, so whatever you think that an NFA is more powerful than a DFA? No, it can do the same thing. Yes, this does it in three things, and with a lot less arrows. This has a lot more complicated arrows, but you know what? Whatever this one can do, that one can do. Okay, let's do another one. Okay, now let's not talk about an NFA. By the way, the book does another example on page 57. Okay, let's do another one. Q1 with an epsilon move. Q2 Q3. That's an accepting state. It accepts 0 is back there. 1 is here. 0 is here. Okay, what language does this accept? We actually did this already. Okay, it has a bunch of 0s followed by a bunch of 1s followed by 1 or more 0s. So this is 0 star, 1 star. We did this 20 minutes ago. 0 plus. Okay, I'd like to make another finite automaton that's built out of this. Okay, we do it the exact same way. Okay, but there's one extra difference because this has an epsilon move. So this is going to be the state that corresponds to the subset of Q1. This is going to be, I'm just doing it the same way as I did this here so that I can find it quicker. Okay, this is going to be a Q3. Okay, and here's going to be the empty state. I'm going to put here Q1, Q2, and Q3. Okay. I do this simply because okay. Question. And this is the main question. If you understand this, if you understand the answer to this, you're perfect. Question: what is the starting state? Stop. Let's ask an easier question. What's the accepting state? Answer: anything that has a Q3 in it. Because if it has a Q3 in it, then that means one of the places I'll be is Q3. So this is an accepting state, this is an accepting state, this is an accepting state, and this is an accepting state. Great. Now, next question. What is the starting state here? It's not Q1. It is not Q1. In fact, you can never get to this state. Why? Because what does this epsilon mean? It means whenever you're in Q1, you're automatically in Q2. So you can never be in the state Q1. Okay, so what's the starting state? Right here, Q1, Q2. Because whenever you're here, you're automatically there. Okay, and now we can start doing it. You ready? You're in Q1 and Q2 and you see a 0. Where do you go? Well, he stays here and he goes here. But one second, when he's here, he's automatically here. Let's do that. We did that a little bit quickly. You're in state Q1 and Q2. You see a 0. Well, the 0 goes here, and when he's here, he's automatically here, so he's 1 and 2. And this 0 goes here to Q3. So you're going to have a map like that for 0. Great. You're in Q1 and Q2, and you see a 1. Okay? Well, if you're here, you're automatically here, but you're here anyways. Okay? And you see a 1, it means you go here, so you go to Q2. But you're off Q1. He sees a 1, he dies. Okay, so things like that. Great. You're in state Q2 and you see a 1. Where do you go? You stay in Q2. You're in state Q2 and you see a 0, you go to Q3. You're in state Q3 and you see a 0. You're in state Q3 and you see a 0, you stay in Q0, Q3. You're in state Q3 and you see a 1, you die. You're in state die and you see, it doesn't matter what you see, you're going to stay there. That's the garbage state. Very good. Okay? Boom. That's a 1. Okay, good. That's taken care of, that's taken care of, that's taken care of. I have to go there. Now we got to do this. You're in state Q1, Q2, and Q3, and you see a 0. Well, the Q3 is going to stay there. The Q2 is going to go here, and you're going to go to Q1. Okay, so you're here. This one stays. This one goes here. And this one stays here. But if you're here, you're automatically here. So that means I stay there. Let's go through that again. The Q3 stays, the Q2 goes to Q3, the Q1 does the Q1, but if he's here, he's automatically there. Okay, so conclusion, it starts off in 1, 2, and 3, it stays in 1, 2, and 3. Good. Let's do this. You're in Q1, Q2, Q3, and you see a 1. Where do you go? He dies. He stays in Q2, and he dies. Okay, and now we're finished. Now again, by the way, I can never be in state Q1 and Q3, because if I'm in state Q1 and Q3, I'm automatically in state, if you're in Q1, you're automatically in Q2. So this doesn't even make sense. Okay? But if you want, we can figure out what it does. Okay? This one does make sense. I could be in Q2 and Q3. But let's see, let's just go through it. If I see a 0, I'm in Q2 and Q3 and I see a 0, he goes to Q3 and he goes to Q3, so this goes to Q3. Okay. I'm in state Q2 and Q3 and I see a 1, he dies, he goes to Q2, so we go here, that's a 1. But again, let's go through this again. These states, we're not going to get there. Okay, we're not going to get there. We're not going to get there. So let's not even talk about that. Okay, so now we have a 3-state NFA with epsilon-moves, and we mimic it now with a 1, 2, 3, 4, 5-state DFA. Okay, and we are now done. I'd like to spend a minute going through formally how this is done. It's on page 55. The formal proof is on page 55, but we still have to describe it. So let's do that. Okay? So the idea is as follows. Your NFA, okay, we're just going to deal with NFA now, is Q sigma delta Q0 F. Okay, and what we're going to do is we're going to formally make a DFA. The main point is that if his states are Q, then his states are the power set of Q. Same alphabet. We're going to make a delta prime. That's going to be the new thing. That's going to be hard. Okay. The starting state is Q0. Okay. And the accepting states are F prime, and I'll show you what F prime is in a second. Well, let's do what F prime is. F prime is equal to those are subset of Q. They're equal to those. What are the accepting states in the DFA? They're those subsets such that F intersect R is not the empty set. In other words, you want to know if this subset is an accepting state? Well, if there's some intersection with the F, if they have something in common, if something of the accepting states, if any accepting states are in R, in other words, the intersection is not 0, then it's an accepting state. Okay, so that's it. Okay, and obviously, as always, the hard thing is the delta prime. And let's show you the delta prime. Okay, I need to draw a picture for a second. Hold on, don't move. Let's get back. I drew some things here. Ready? You have an NFA, states, symbols, transition function, starting symbol, the accepting states. Then we make a DFA out of it, where the main idea is what the states here become subsets of the states here. The same alphabet, different transition functions, Q0, F prime. And I showed you what to do. Now, let's talk about the transition function, because that's the only thing left here. We have to explain what the transition function is. The transition function takes a subset of states and a letter, and it gives you out a subset of states. Okay? Now, let's do it. Let's do it. For example, if you have, okay, so here's, let's say this is part of your NFA, okay, and it says if you're in state Q31 and you see an A, you go to Q54, you go to Q62, and you go to Q53. If you're in state Q68 and you see an A, you go to Q21 and Q39. If you're in state Q91 and you see an A, you go to Q62, Q39, and Q99. I'm making this up. Okay, question. What happens now in the DFA, okay, and you're in state Q31, comma, Q68, comma, Q91. Okay? You're in the state that has this guy, and this guy. Where should you go? Okay? And it's very simple. You go to where this one tells you to, where this one tells you to, and where this one tells you to. So basically, and that's a DFA. That's a one, with one letter, you go to the whole state that has, let's do it carefully, Q54, Q62, Q53, Q21, Q39, Q62, oh, we have Q62, Q39, we have Q39, Q99. Okay, so that state takes you into that state. And again, this is deterministic. With one letter, you go into the subset state of subset, the set of subsets that you can. Let's be formal explaining, now that we understand what you're doing here, okay, let's be formal. It's as follows. R, a subset of states. Delta prime on R, that's what it does, it takes a subset of states, and a letter, okay? And what does it output? It outputs a set of states. So which one is it? It's the union of little r in R. In other words, this guy, and this guy, okay? And you look at the delta of little r, comma a, and you go to all this. Now this is an NFA, okay? So it's going to give you a set. Here's the set that corresponds to Q31. Here's the set that corresponds to Q68. Here's the set that corresponds to Q91. Okay? And you go through each one of the elements in there, and you say, okay, what's in this set, what's in this set, what's in this set, and take the union of all of them. Okay? And that explains how you get delta prime. That's a formal way of getting delta prime from delta. Okay? I told you this. It's not, we understand how to do it. We did it over here. You all followed that very well. But part of this class is to show you how to read a formal text. And so we're reading a formal text. Make sure you understand how to do this. Make sure you understand this. Okay, great. Now, let's put this all together. What did we learn today? We learned that you give me an NFA, I can make a DFA out of it. Okay, theorem. Let's write it up as a formal theorem. A language is regular. What do I mean by a language is regular? That means there's some, we had a definition of that. It was the first day of class, section 1.1. What does it mean for a language to be regular? There's some, what we call now a deterministic finite automaton that recognizes it. Okay? Great. A language is regular if and only if some NFA recognizes it. A language is regular if some NFA recognizes it. Okay? Now, this is an if and only if, so it goes both ways. Okay? Let's go this way first. A language is regular means there's some DFA that recognizes it. Well, what did we say? Here's the set of all DFAs. Here's the set of all NFAs. So, if a DFA recognizes it, then definitely an NFA recognizes it. And we just have to remember, we have to go through this again. Why is this a special case of this? Because DFAs are NFAs where the set that you go to has a singleton element. Just one element in it. Okay? So, in an NFA regular, you can go to a set with 10 elements, you can go to a set with no elements, you can go to a set whatever you want. But in a DFA, there are special types of NFAs where you can go to just one element. So look what this says. A language is regular, that means a DFA. That's the definition, a DFA recognizes it. Well, if a DFA recognizes it, a DFA is a special type of NFA, so then an NFA recognizes it. That's very simple. Now let's go this way. If some NFA recognizes it, well, guess what we did? What we did for the past 20 minutes was show how do we build, we can construct a DFA that, the whole point is we had a DFA that does the same exact language. So if this language is recognized by an NFA, then there's going to be a DFA that does the same exact language. We can construct a DFA that recognizes the same language. Okay? So we can construct a DFA that recognizes the same language. So if an NFA recognizes it, then it's also a regular language. Great. Don't move, because we actually proved two theorems today. Okay? We didn't only talk about NFAs, we also talked about Epsilon-move NFAs. Okay? And we said those are even larger. Epsilon-move NFAs, those are even larger. And again, the theorem goes both ways. Okay, very good. So it goes both ways for NFAs, and it goes both ways for Epsilon-move NFAs. Great. Now, we're going to draw a picture. And I told you about this picture the first day of class we're going to draw this picture. We're going to draw it the last day of class. Okay? We're going to build up this picture. We're going to see it over and over. Okay, but now we can really get it. Okay, let's go through it. Sigma, an alphabet. Sigma star, set of words. Power set of sigma star, set of languages. Okay, we did this every day. Okay, by the way, sigma is finite. Sigma star is countably infinite. We'll understand what that means later. And the power set of sigma star is uncountably infinite. So there's a hell of a lot of languages. But we're interested in special languages called regular languages. Okay? And each one of these is a subset of words, is a language. Great. And I drew this already. This corresponds to DFAs. Let's go through. The definition of a regular language is a language that a DFA can recognize. Very good. But now we saw something else. We souped up our DFAs and we got NFAs. We souped up our NFAs and we got Epsilon-move NFAs. I'm just going to write it as Epsilon NFAs. Okay? Now, what was the purpose of this theorem that I just erased? Well, the purpose of the theorem was says, look, whatever can be done by a DFA, by an NFA, can also be done by a DFA. So we don't gain anything bigger by getting these new languages. It's the same thing. Okay? Okay? Whatever an NFA can do, a DFA can do. Whatever an epsilon NFA can do, so it's the same set of languages. Okay. Now, let me just foreshadow a little. We're going to go bigger and bigger. We're going to find more and more complicated languages. And guess what? We're going to get more and more complicated computers. And this is that thing that we told you. Formal language theory is about the relationship between machines and languages. Languages and machines. Okay, that takes care of that. Okay, great. That's a very pretty picture. Keep it in your head. Understand it. Okay, great. Next. Okay, we're not finished with section 1.2. There's a lot more stuff. What we're going to do now is talk about operations on languages. You know what an operation on number is. You take one number, you take another number, you can add them, you get a number. 5 plus 2 is 7. Okay? There's other operations too. You can multiply. 5 times 2 is 10. Okay? 5 divided by 2 is 2.5. 5 minus 2 is 3. Okay? There's 3 operations. There's many operations on numbers. We're not interested in numbers. We're interested in sets. We're interested in languages. So what we're going to do is we're going to talk about how we can do other types of things with languages. Okay? So I want to talk about some operations on languages. In particular, I'm going to talk about three operations on languages. Let's do an example first. Here's a stupid language. We're going to deal with stupid languages. XX, life, smile. That's a stupid language that has 3 words. Here's another language, K. It has the word dog. It has the word big. It has the word happy. And it has the word BC. That's my stupid language. I can call it. I can put in anything I want. Okay. I want to show you 3 different operations on this. The first operation is called union. And it's the simplest thing possible. Take L, union it with K. That means those words that are in here or in here. Can't get easier than that. So this is XX, life, smile, dog, big, happy, BC. Okay, that's a very simple operation. Just take What's a language? It's a subset of words. Union this subset of words and that subset of words, and you're done. 2. Concatenation. Okay, this is a little bit more abstract. This is something you didn't think of. I know what concatenation of two words are. You give me a word here, you connect it to a word here, you put them together, and that's called the concatenation of two words. But now we're talking about the concatenation of two languages. What's the concatenation of two languages? Well, it's basically L1 L composed of K is equal to, let's write it up like this, W such that W equals W1 concatenate W2, where W1 is in L and W2 is in K. Okay, so it's those words that are, the first part of the word is from L, the second part of the word is from K. Okay, let's do an example. In this case, it's as follows. L composed K is equal to XX dog, XX life. Sorry. XX big, XX happy, XX BC, life dog, life, I'm getting bored, big, okay, that's one word, life happy, etc., etc. Okay. How many, by the way, the union is going to have less than, it could have overlap. There could be words that are in the same words in both of them. So that's the concatenation is going to have, if there are 3 words here and there are 4 words here, they're going to have 12 words. Okay, great. Next, the third operation is called the star operation. It's also sometimes called the Kleene star operation. Okay, and it's as follows. It takes only one language, and you get out L star. Okay? Okay, so let me just tell you what it is. L star is the empty word. Union L. So it's got the language in it. Okay? It's got the same words as L does, but it also has the empty word also. One second, we're not finished. It also has words that start at L and end, have 2 copies of L. They're also L composed, L composed, L. 3 copies of L. And L composed, L composed, L composed, L. 4 copies of L. Union, dot, dot, dot. So the star operation is any amount of L's, any amount of copies of L's that you have. Let's do L over here. Let's do L star over here. You ready? L star is equal to the empty word XX life smile, but also XX 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 life XX smile. Let's do some weird ones. Smile, life, smile. It's one giant word, etc., etc. L star is an infinite language. No matter how big L is, L star is an infinite language. This, well, the other operations, well, if you start with an infinite language, you can get to an infinite language. But this one, even if you, no matter how small you start with the language, you still get it. Okay, great. Let me just tell you where you've seen this star operation before, because you saw it the first day of class. You ready? First day of class I said, you know what? That's a set of symbols. Well, we called it an alphabet. Let's say we didn't call it an alphabet. Let's say we called it one-letter words. Well, in that case, one-letter words, star, is all possible words. Concatenation of all possible letters in that sigma star. So it's the same type of operation. Just here we thought of this as a bunch of symbols, and here we think of this as a bunch of words. But one letter words It could be the same thing. So it's the same type of thing. It basically as many copies as you want of thing. Another way to think of it is, if you think of L to the fourth, let's say, as L composed, L composed, L composed, L. So then L star is the union of n of L, n greater than or equal to 0, of L to the n. Okay, many copies of itself. Okay, great. So these are the operations of languages, and nothing hard here. Okay, great. Now I have to talk about, this is what we talked about in operation. An operation is just a function that takes two things and gives you another thing. Okay, great. Okay. Now I have to talk about what does it mean for a set to be closed under an operation. What does that mean? To a set to be closed. What's that phrase mean? Okay, so I want to again back up to numbers because we like numbers. We did numbers in elementary school. Okay, we want to talk about numbers and do it. So let's do this. You ready? The natural numbers, that's whole positive numbers, is closed under plus and times. Let's see what that means. What that means is take a natural number, take another natural number, add them, guess what you get? A natural number. Take one number, a natural number, take another natural number, multiply them, 5 times 3, 15, a natural number. Okay? In contrast, n is not closed under subtraction and division. Why? Very simple. Yes, 7 minus 5 is 2, is a whole number. That works. Okay? We start off with a natural number. We take another natural number. We subtract them. We get a natural number. That works. But watch what else can happen. 5 minus 7, you get negative 2. Negative 2 is not a natural number. You've gone outside of the set. So we think of the natural numbers as a set, and if you take two of the elements in there and you do the operation, the minus operation, you get something outside of it. So it's not closed within the set. You have to go to outside of it. Okay? Great. Let's talk about z. Z is the whole numbers, positive or negatives. Z is closed under plus. Take two positive or negative numbers, you're going to get a positive and add them, you're going to get a positive or negative number. Multiply them, you're going to get a positive or negative number. Subtract them, you're going to get a positive or negative numbers. 5 minus 7 is negative 2. That's a positive or negative number. Okay? But z is not closed under division. Okay? When you do division, you get outside. 5 divided by 2 is not an integer. 5 divided by 2 is not an integer. You get it. Great. Q, fractions, is closed under, take any fraction, positive or negative fraction. It's closed under plus, times, minus, division. Take two fractions, divide one by the other. You know how to do that, you get a fraction. Okay? But what is Q not closed under? Q is not closed under taking the square root. Okay? There's a theorem, it says as follows. The square root of 2, that's a rational number, is not equal to a fraction. Okay? And we can go on with this. We're not doing anything with numbers here in this class, but I just want to show you what the word closed means. The word closed means is if you take the two things in there, in the set, and you do the operation, you get in the operation. You get in there. So let's just look at this. Here's Z, here's Q. Okay. This big set Q, you do all the operations in the set Q, all these operations, you're going to land in here. But you know what? You take a square root of something in here, like 2, you could land out here. We'll call this the real numbers, which is that. Okay, sounds good? Okay, we're not interested in numbers. We're going to talk about sets. And we're going to prove theorems about sets. Sets of words, that is. Sets of words. What do we call sets of words? Languages. So let's go through it. You ready? Theorem. Regular languages are closed under union. What the hell does that mean? Okay, we're going to go through it very slowly. I'm add our ink with this one. Fix that later. Alright. Okay. Well, what that means is, if you take a regular language and you take another regular language, well, hold on. If you take a regular language, that means there's a finite automaton that accepts this, and you take another regular language, there's a finite automaton that accepts this, then you take the union of them, then there's going to be a finite automaton that accepts that. Okay, let's do this carefully. Whoa, bad. Let L1 be recognized by M1. Let L2 be recognized by M2. Okay? So we have 2 regular languages. Okay. Conclusion, then L1 union L2 will be recognized by M3. Okay. What's M3? Well, I'm going to draw a picture of this, and then we're going to be formal about it. So let's do M1. M1 is a nice machine that recognizes L1. It has a starting state and arrows here, and this could be an epsilon move, whatever you want, and it has accepting states. Great. Okay, next, M2 is another machine, and it also has a starting state, and it's probably totally different than this one. It should be totally different, and lots of different states, and it has accepting states also. Okay, now what I want to do is construct another machine called M3, and M3 should recognize words that are in this language or this language. In other words, I want to be able to put into this machine, M3, a word, and it should tell me, hey, is this word in here, or is this word in here, or is it in both? I don't mind if it's in both. Okay? And so it looks like this. Here's the machine. This is the machine M3. Okay. And now this machine, what it does is, at some point, you start off here, and automatically you start here and here. Automatically, because the epsilon-moves takes you here and here. And now you read the letters of this word, and you're going to bounce around here and come to a conclusion about this, or you're going to bounce around here and come to a conclusion about this. And if you land in on any of the accepting states here, it's accepted. If you land in any of the accepting states here, it's accepted. If you land here and here, after reading the words not in an accepting state, the word's not accepted. Okay? That's your machine. And it makes sense. Okay, now we have to be a little bit formal about this. We have to be a little bit formal about this. Again, the purpose of the book is to teach us how to be formal, so I'd like to be very formal about it. Okay? But the picture is the giveaway. So let's keep an eye on the picture and then we'll draw it. You ready? Let's assume M1 is equal to Q1, that's the set of states, comma, sigma, that's the alphabet, we're never changing the alphabet, delta 1, comma, Q1, that's the starting state here, Q1, okay, and F1. And M2 is Q2, okay, F1 is the accepting states of this. Machine M2 is Q2, a set of states, sigma, an alphabet, delta 2, transition function, Q2, that's this state right here, Q2, that's the starting state of this machine, comma, F2, that's these two accepting states, the accepting states for this machine. Now I want to do this and I want to show you what M3 is. So let's write it out formally. M3 is as follows. Okay? What's the states in this big machine? Look at the picture and tell me what the states in this machine is. And the answer is, it's Q1 union Q2 union a new state, which let's call it Q0. Q0. That's an amazing thing. So we looked at this picture, we see what's this new machine has? Well, it has these states, and it has this new state. Great. Now, we're describing M3. We're formally describing what this machine is. What's its alphabet? Same alphabet as before. What's its transition function? That's going to be hard, so we're going to save that for later. That's delta 3. Great. What's its starting function? The starting function of this was here. The starting state, what's its starting state? The starting state over here was Q1. The starting state for here is Q2. Okay, what's the starting state for here? Answer, Q0. Q0. Great. Great. What's the accepting states for this machine? Well, it's very simple to see. The same accepting states here as the same accepting states here. So it's F1 union F2. Okay, that's it. Finished. But we got to do the transition function. And the transition function is slightly more unpleasant, but doable. You ready? We do it as follows. Delta 3, you give me a state, you give me a letter, I'm going to tell you where to go. But there are 4 possibilities. Okay? And the 4 possibilities are not complicated. One of the possibilities is that if Q is a member of Q1, if your Q is over here in this thing, then here's what you do. You ready? Then you do delta 1, because you're in this machine, you should do what this machine tells you to do. Delta 3, the transition function for this whole box, either does what's in here, or does what's in here, or we have to worry about that. So, look what delta 1 tells you what to do. On letter Q, on state Q, delta 1. That's simple. Great. What's another possibility? If Q is a member of Q2, that means it's in this box, then you should do what delta 2 tells you what to do. Okay? And by the way, this could be an element, this could be a set, this could be with transition functions. This is a transition function. Okay, next. Great. What happens if Q, if it's not here, and it's not here, what is it? If Q is equal to Q0. Okay, great. And A is equal to the empty word. Where should you go? And the answer is very simple. Q1, comma Q2. If you're in Q0 and you see the empty word, you go to Q1, union Q2. Okay, that's simple. Finally, one other thing. If Q is equal to Q0, you're at your new starting state, and A is not equal to epsilon. In other words, if it's something else, if you're in here and you see a letter, well, just ignore it. Die. Okay? So that gets everything there. Let me just make sure you can see everything. Yeah, you can see everything. Okay? So this is a theorem. Okay? It says regular languages are closed under union. That means do one, do another, you get it. Okay? Okay, let's just go through it again. Here's M1, here's M2. We build M3 out of M1 and M2. Here's what the machine is. The hard part is the transition functions. The transition function basically does the transitions in here, or the transitions in here, or go like that, go to both. Okay, very nice. Let's do another theorem. Ready? Not hard. Regular languages, you have to rewrite. I don't have to rewrite because I have a whiteboard, so you have to rewrite. Regular languages are closed under concatenation. Concatenation. Let's see why. Okay. Let L1 be recognized by M1. Let L2 be recognized by M2. Then L1 concatenate, not union, concatenate L2 okay. L1 concatenate L2 will be recognized by M3. Let me draw a picture of what M3 is, and as follows. But first let's remember what this language is. What's L1 concatenate L2? Well, it consists of words that start off in L1 and then continue on to L2. That's great. Okay? So it consists of words that, here's your machine M1. It's got a starting state, it's got lots of other states, and it's got accepting states. Okay, and it's got lots of arrows all over. Okay, great. L1 composed L2 will be a word that starts in here, finishes in this machine, finishes at accepting states, and then I want it to, the second part of the word should work in M2. It should work in M2. And again, there's arrows all over. I'm not interested. Okay, but what I want is that when you're finished reading a word that's in L1, you should automatically start reading a word and see if it's in the second part is in L2. And so what we do is as follows. From the accepting states of M1, I want you automatically to go to the starting states of M2. Now, this big machine, we're going to call that big machine M3. Okay? So what does M3, I'm not finished yet. What does M3 do? It reads in a word and sees if the first part is in M1. If the first part's in M1, then it automatically goes to M2 and sees if the second part is in M2. One problem. Okay? These are no longer accepting states because we don't want words that just belong to L1. We want words that start in L1, okay, but finish in start in L1, but finish in L2. And so those are no longer accepting states. Okay, let's start off being formal about what M3 is. M3 is equal to, you have Q1, the set of states in here. You have Q2, the set of states in there, comma, sigma, it's the same alphabet always, comma, delta 3, that's a little bit more painful. Okay, what's the starting state? Well, this is Q1 over here. The starting state is going to be Q1. We start by reading in a word from L1. Okay? Great. What's the accepting states? Not these guys, but these guys. F2. Okay? And the transition function delta 3. You can read the transition function. I think it's on page 61. They do the transition function. Basically, but read it, because I'll ask it on the test. But the main point is, look at this here. Okay, and you can figure out what it is. Very good. Next. By the way, on a test, I might tell you, prove something formally, and do not give a picture. Okay, so let me tell you how to cheat. If I tell you don't write a picture, here's what you do. Take another piece of paper, write a picture. Okay? Because you think in pictures. Once you have the picture written down, then you can be formal about it, look at the picture and see what you want, what you don't want. Okay, great. Okay, a few more operations. Guess what the next one is? Regular languages are closed under... Now let's erase this whole thing. Closed under the star operation. Okay, they're closed under the star operation. Let's see why. Let L1, I don't even need L1, let L be recognized by M1, and M1 is a machine. Okay, you know what, let's just leave out the M. Let's just leave out the 1. It has a set of states, it has an alphabet, it has a delta, it has a Q0, okay, it has an F, etc., etc. Okay, now I want to create then L star will be recognized by M star. I'm making a new machine. Guess what? The machine will be built out of M, but it's a new machine. And here's the machine. You ready? Here's machine M. It has a starting state, it has lots of other states, it's got arrows here and there, okay? It's got accepting states. Okay? What does L star contain? Let's remember what L star contains. L star is equal to the accepting state. It's equal to the empty state, the empty word, comma. Let's do it like this, sorry. The empty word, union L squared, union L to the third, union L to the fourth, dot dot, union dot dot dot. Okay? So the first thing first is L star has the accepting state. I don't know that that's an accepting state over there. That's a starting state. I want to make sure that the accepting state is let in. So here's what I do. I make a new starting state. A new starting state. Okay? And the new starting state automatically is an accepting state, and there's an arrow going into the old starting state. That way, this thing is in. Great. Now, the word is, if the word is the empty word, it's accepted. If not, it goes on and bounces around in here. And when it finishes, if it lands in here, in one of those accepting states, it's an L. Okay? But I don't only want L, I also want L squared. So here's what I do. From the accepting states, I go back around to the starting state, the old starting state. Okay? And we bounce, the second part of the word, we bounce around here and see if we land over there. Okay? And if we do, we go back again and try the third starting state. We go again and try for a third part of the word, and a fourth part of the word, and a fifth part of the word, etc., etc. This whole machine is called M star. Okay? Let's start off being a little bit formal. Okay, I'm not going to do the whole thing. M star has the same states as before. Look at the picture. Union, another state. we'll call it Q0. This is Q1, this is Q0. Very good. Next, same alphabet. Next, delta, we'll call it delta star, a new transition function. Next, what's the new starting state? Oops, this should be a Q1. The new starting state is Q0. Next, what's the accepting states? The same accepting states as before, but this new one. So it's F union Q0. Okay, and I'm going to leave it to you to figure out what L star is. Basically, it's if the element's in here, then you do this. Otherwise, don't forget to do this transition function. It's on page 62 and 63 in the book. Okay, so that's a lot of work for section 1.2. But we have this new thing called nondeterminism, and we saw amazing things that we can do with this nondeterminism. We saw how we can use this nondeterminism to do all types of operations on sets. I'm sorry, I'm not finished something. We have 2 more operations, but they're easy. Okay? The book doesn't do these 2 operations, but we're going to do them, and you are responsible for them. And they're very simple. They're very simple indeed. You ready? Regular languages are closed under hold on, I forgot the word. Complement. Sorry. Complement. Okay, let's remember what the complement of a language is. If you have a bunch of words, then the complement is written like this. That's those words that are not in the language. And we saw how to do that. We saw that in the first class, right? We saw that complement, those things not in the language. How do you do it? Well, you basically swap those accepting states and non-accepting states. Remember, we did a lot of examples of this, and there's more examples of this in the homework. So let's just say, if M is equal to Q sigma delta Q0 F, then M bar, if L is recognized by M, then L bar will be recognized by M bar, okay? And what is it equal to? Same states, same alphabet, same transition functions. Don't change anything in the same transition functions. Don't change the starting states. The only thing you do is, what was an accepting state is now not going to be an accepting state, and what was a non-accepting state is an accepting state. So Q minus F is now the new accepting states. Take all the states Q, pull out the things that are F, that's the new accepting state. So if you start off, L is a regular language, in other words, a finite automaton can recognize it, then L bar is also a regular language. That's a very pretty thing. We did that the first day of class. Great. One more operation. Okay. Regular languages are closed under intersection. Okay, now we never even talked about intersection, but we know what it is. Okay, it goes as follows. If L1 is a regular language, then L2 is a regular language. The intersection of L1 and L2 is a regular language. These are words that in here and in here at the same time. Okay, that's very nice. So how do we check if it's in there and in there? Okay, I want to go and talk about politics for a second. Okay, and it goes as follows. You ready? If I'm asking for female and Democrats, okay, I'm asking for female and Democrats. Let's talk about politics. I want to look at the set of all female Democrats. Another way we can do this is what's called De Morgan's law. We can say, okay, look at those people that are not female, males, leaving aside political correctness for a second, okay, union, those people that are not Democrats, Republicans, okay, leaving aside independents, okay, take this and look at that. Take the complement of that. Let's see what this corresponds to. It corresponds to as follows. Let's say it's as follows. Female and Democrat. If you're female and Democrat, that means you're not male or Republican. Okay, so let's put that another way. You're not male or Republican. If you're female and Democrat, that means you're not male or Republican. Okay, now we could do the same thing over here, but this rule is just about sets of things. Okay, the intersection female and Democrat means you're not female or not Democrat. Okay, same thing here. Okay. If there's a word that's in here and in here, that means the word is not in here or not in here. Okay. Now, since we know how to do union, I did that 10 minutes ago, and we know how to do complement and complement, we know how to make a new machine. So I can make a machine using these old things, using these other operations. So intersection, I can do intersection by using complement and union to get intersection. It's a very pretty thing. Okay, that's the end of section 1.2. We'll move on soon. Okay, thank you.